In this video, we are going to talk about how chips are manufactured. Is this what we are going to talk about, Heather?
Yes.
And so why you are the right person? You are actually working in chip manufacturing, correct?
Yep. Yeah, so I have a background in mixed signal design. I worked in test and measurement for several years, and right now I work as a solutions engineer. So I help customers that are designing in a foundry process. And so I get to work very closely with engineers that do everything from manufacturing to product testing. So it's very exciting.
Cool. So where do we start? What do we need to understand before we actually start talking about how chips are manufactured?
So I come from a design background, so I like to think about a schematic first. So I would first think about a circuit that I was trying to build. And so I wanted to start here with us with an example of an inverter.
Mm-hmm.
So a CMOS inverter, as you know, has like a PMOS and an NMOS device. And they're really cool because it has low static leakage because one of those devices is basically always off, except for a really small time when you're transitioning high or low, right? And so if you start by thinking about a schematic and you say, okay, how would I physically build this inverter in the fab? I think that's a good place for us to understand what we want the layers that we're trying to build on the silicon to look like.
Mm-hmm. So you already mentioned silicon, so that's the basic material. And I think you had a nice picture of this. There is
Yes.
the tube or what? This one. This is
Yeah.
exactly what
Yep.
I meant.
So this is really cool. So these are called silicon boules, and they grow these, and the crystal lattice here is like perfect. So these are grown. These are really long, beautiful boules, and then they're sliced into silicon wafers, and that's your starting material. That's not the starting material for everyone. Like if you're doing an RF application, you probably wouldn't pick silicon, but for CMOS fabs like TSMC and Micron and things like they use a lot of silicon, and that's throughout the industry the most ubiquitous starting material.
Mm-hmm. And I think there are different sizes of these.
Yep. So the way that typically we'll talk about a fab is we'll talk about the size of the wafers that get processed. And so here's a picture. By the way, this is one of my pet peeves working in the industry is pictures of people holding wafers. I don't know why these are everywhere, but they drive me crazy. Like it's like, oh no, please put the wafer down. But this is a 300 millimeter wafer. 200 millimeter. So that's kind of a common number. So like 11 or 8-inch or 6-inch wafers. And typically it looks something like this, and you'll have what are called like scribe lines or streets. So you'll have your die, and then you'll have areas of space in between each die, and that's where you're going to dice through so that you can singulate the wafer into smaller chips.
Mm-hmm.
And interestingly, that's in those scribe lines is where you put a lot of the test structures and things you need to use in the fab when you're doing like inline electrical testing to make sure the process you're building in the fab is basically centered with your target specs.
Mm-hmm. So basically, when chips are built, it's not only the chip itself. There are also some other circuits which are helping with the process and testing.
Yeah, yeah. So on a wafer, typically what you would have is you would have the chip that you're trying to build. In the streets, you're going to have test structures that you're going to be measuring throughout the processing. So these could be like serpentine metal lines or cone lines that go like this, where you're measuring like breakdown voltages or resistance of via chains, things like that. And then you're also going to have alignment structures. So these are like interesting shaped structures. They might look like a cross or a hashtag. And those are alignment structures that the lithography tools use to make sure that as you're building up the layers, all the layers are aligned
Mm-hmm.
correctly to one another. So you'd have the design from the customer, the test structures that the foundry needs to make sure for monitoring, and then you'll have alignment structures. Those are kind of the three components you'd have present on a wafer every single time.
Mm-hmm. Okay, so we have the silicon. Now,
Yep.
what is the next step? They will cut it into this. It's called wafer. Yeah.
Well, actually, so yep. So the first thing is you'll have this giant silicon bowl. They'll slice it up. They'll have these silicon wafers. This
Mm-hmm.
is called a boat right here. The silicon wafers are transferred around in boats. And basically it's going to go into the fab and we're going to start the processing on it. And so the first step you actually do is you'll do like a quick clean just to make sure there's no like oxides growing or there's no, guck on your wafer. And then you're going to grow what's called a buried oxide or a pad oxide, and that's going to protect your silicon layer because that silicon layer it's a crystal lattice, right? So it's perfect. There's no damage, and so we have to like treat it very carefully because if we don't, there's dislocations and things that can occur that can cause like noise and other problems for us later. So that's that SiO2 layer that you see here
Mm-hmm.
on the right. You see this thin layer. That's actually going to be there for a long time throughout the processing just to protect the silicon. And so the way that fab processing works is we just do the same sequence over and over again to build up the layers. We do a lithography step where we have the wafer, we squish on this like spin coat of resist. That's this right here, resist coating of a wafer.
Mm-hmm.
We're going to spin that on. We're going to expose a reticle that has the shapes that we want to print on the wafer. We're going to expose that with UV light. And then what it'll do is we can develop the resist and it'll leave behind patterns for us that we can then use to shape whatever layer we're working with. So it'll always be like lithography, then a deposition, and then a lithography, and then an etch, lithography, and then doping. And we just do that over and over again until we've built up this entire stack of layers that will form a transistor or diode or resistor or whatever we're trying to build.
Mm-hmm. You already mentioned a couple of words like doping, and I don't
Oh,
know. So
no.
what are
Yeah.
these?
Yeah, it's a so doping is this is a fun one. So semiconductors are called semiconductors because they're like semi good at conducting electrons, right? So we like to mess with our semiconductors, right? So we can either add more electrons. So we'll add atoms in the lattice that can donate an electron. These are called donor type. These are N type. So basically we're putting extra electrons in the material to make it more conductive, or we can add acceptor type or P type materials. Now, interestingly, the way we dope things is like it sounds kind of brutal actually. So you either put the silicon in a chamber, right, and you heat it up really hot and you expose it to the ions you're trying to implant, or you just legit blast it with an ion implanter, right? So you're adding these either donor or acceptor type atoms because we're trying to change the conductivity of the
Mm-hmm.
material. And when we do that, we can create these P-type and NMOS devices. So on the right here, for example, I have an NMOS device. So I have N-type source and drain regions that when I turn my transistor on, current can flow between those two regions under the gate. So current's actually going to flow from this. Can you see my mouse?
Yes, I can.
Oh, great. So it'll flow from like, for example, from the drain, it'll flow under the gate to the source right over here. And then again, for the PMOS device, these P-type charge carriers would flow from the source to the drain. Now, the cool thing again about CMOS is we can make both of these complementary devices in the same substrate on the same wafer. And that's really the power of CMOS transistors, right? Is that you have both types of devices that you can use to build every kind of logic gate you could think of, amplifiers, digital to analog converters, everything.
Mm-hmm. So I always imagine they just expose it to some kind of gas, and this gas will change this material. So it doesn't have to be gas. Yeah, you can just do what is it like some kind of laser, or I have no idea.
Yeah, the ion implanters are pretty interesting. I don't know if I have a picture of one. I don't think I did. I should have put a picture in here. The two ways you can do it are you bombard it with a beam of ions. That's this
Mm-hmm.
one, right? Or you diffuse it, and that's what you were thinking of first is the diffusion method, right? Where you
Mm-hmm.
put it in a chamber, you heat it up, and then you just stream in the gas, right? And then that those ions will like diffuse into the silicon.
Mm-hmm. And so you have to do this in two different steps. So first you put there the mask and only uncover the areas for the N type. You do it, and then you cover it again and make opening for the P areas and do it.
Yeah, exactly. So do you want to go through a couple steps and we can see how this
Yeah,
comes
okay,
together?
okay.
Okay, so we're gonna start by this is again, this is our inverter, and here is what the end product is gonna look like is this cross section at the end. So a couple of a term that we use a lot in manufacturing is cross section. So that's like if I'm looking at the wafer and I cut it and then I flip it. So it's like imagine like a hamburger, right? And you cut it and you look at it before you take a bite. Like that's what we're doing with the transistor right here. So this is a cross section, and this tells us all the different layers and kind of the, what they look like when they're formed. So we can start by trying to build this inverter. And first we're going to use a mask. So we're going to spin the photoresist.
I have a
Yeah.
question. You already call
Yeah.
it P substrate, so it's not silicon?
Well, it is silicon, but it's doped with P-type material.
Oh, so there is one
It's
more
doped,
step
so it's
before
P-type.
we do
Well,
everything.
it shows up to the fab as a P-type silicon substrate.
Okay.
So typically, like you might have multiple vendors that you use, but they'll all have like pretty similar specs. So you'll like have a particular a doping and like a resistivity requirement coming from your manufacturers. So it shows up as P-type material, P-type, and I'm sorry, I'm going to use the word substrate and wafer interchangeably,
Okay.
but it means the same thing. So, this is your P-typed silicon starting material that showed up in your fab. We've added this box layer. So again, that's this thin layer of oxide that we're using to protect that pristine silicon surface. Then we're going to spin a resist layer, right? We're going to shoot through our N-well mask, expose it, and now we have this shape right here that is the shape of our N-well. And then we go ahead and dope it. So we're going to either bombard it with ions or, use a diffusion process to create this N-well. And basically that's N-well is a more lighter doped N material. And this is, again, if you look up in this cross section, you can see this is where we're going to create our PMOS device. So after we have that,
I have another question. So you remove the photoresist before doing the doping?
Yep.
Oh, okay.
Well,
Interesting.
oh no, I'm sorry. Not before you do the doping, after you do it, because you're going to put on a new layer of photoresist for the next step.
Oh,
So the photoresist can act like a blocking layer, basically.
that's why I asked, because there is also the other blocking layer, the SIO layer.
Yeah.
But you always make opening in this SIO layer when you put there the
Yes.
photoresist. Okay, I understand
Yes.
now. I understand now.
And there are, I'm oversimplifying the fabrication here, but you bring up a really interesting thing, and I think you probably have an intuition for it, is we actually use what are called screen oxides throughout the process. And that's basically a really thin layer of oxide that will dope through, will send the ions through. And again, that's to protect that silicon surface. So screen oxides are used a lot by us when we're fabricating these, but I didn't go into that level of detail just because I wanted to make sure we
Okay, yeah. I was just
see
curious.
the big picture. But that's a good intuition you have. Okay, so if I were just thinking about drawing this inverter on a layer, the mask that I would need, this N-well mask, so I'm trying to keep track of the masks that I need to create it, it would have this shape.
This
Makes
is
sense?
this is
Because
the
we
view
created.
from the top, basically.
Yep, exactly. So we're looking cross section as we build it up on the wafer, and then top down, here's what it would look like. Then moving on, we're going to do a gate oxide. Now, the gate oxide, I have a animation, so let me try to do this real quick if I can try it. So source drain regions are separated by what's called a channel underneath the gate of the device. So you have the gate, a gate oxide, and the silicon. The silicon is conductive. The gate oxide is an insulator, not conductive. And the gate, this is a polysilicon, so like fake silicon, also conductive. So think metal, insulator, metal, right? So a useful way to think about a transistor is like a switch. When I don't have any voltage applied on the gate, I have an oxide in between the gate and the silicon. This is a open switch. That's what I've shown here. Then if I apply a voltage to the gate, it's like my switch is on and I can have current flowing from the drain to the source. This is for an NMOS device. There's a couple interesting things about the gate oxide. So typically the gate oxide is really thin. It's like in the nanometer range. And what we want to do is we want to be very protective of the interface between the silicon and the gate oxide that we're growing on top. So typically the gate oxide is grown, and that's important because of like the crystal alignment, right? Because we want it to be aligned with the silicon, and then it grows and it's very pure. And you can grow it in under different conditions. So that's why I talk about like dry or wet conditions. There's a lot of like chemistry that goes into this that's really interesting. But the purity of the gate oxide and the perfection of the silicon wafer itself is actually really important. Because if you don't have that, what happens is you have places that electrons can get trapped in, and then it can show up as noise because occasionally the electrons will get untrapped and then you get more or less current flow than you were expecting and show any I don't want to say dislocations, that's not the right word, any imperfections in that silicon dioxide interface causes places for electrons to get trapped. So we got off track, but
No. It's interesting.
yeah, so we grow this thin gate oxide layer right here, and then there's the polysilicon gate. And then we're going to, again, do a resist coat. We're going to expose the resist with this poly mask. So that says, what shape do I want my polysilicon to be? And then I end up with the polysilicon gates. And so if I were just looking top down, this is what my poly mask might look like. So now I have a couple layers. So I'm just going to keep building my transistor. So next I'm going to define where my source and drain regions are for my NMOS device. And then also a connection to the body of the PMOS device. So what you need is you need like an N plus to connect to the N well. That gives you like a low resistance contact. And so that's what you see here. You see the N plus region and then an N plus connecting to the N well. So this allows you to control the voltage of the body of that PMOS device. This is important because one of the things we haven't talked about yet is, I said you can think of the devices, the FET devices as a switch, like on and off. Well, that switch actually has a threshold. Like imagine you're turning on a light, like an old school toggle switch, right? There's a point where it just clicks on, right? Like there's a threshold voltage for the FET where it will start to conduct. That's we call it the threshold voltage. And if the body of, or the N well, for example, of the PMOS device or the NMOS device, if the bias of that changes, the voltage present in the body of the device changes, the threshold voltage can shift. So it's really important because if you're trying to make an amplifier, right, and you've biased it perfectly and you're like, okay, it's going to turn on at this voltage, I'm going to get this much current, and your like body voltage is like slowly floating higher and higher, then your threshold voltage shifts with it. So
I have a question. So then does it mean it's more difficult to build kind of analog chips than digital chips?
You're going to get me into so much trouble. But yeah, it's way harder. No, I shouldn't say that because digital designers have their own like, there's a lot of like signal processing and Verilog coding they have to do. So I shouldn't be too hard on them. But yeah, I feel like analog is way harder. Like it's an art, right? It's like, the greats in analog design were just these incredible, like, you kind of have to be a tinkerer, I feel like, to be an analog designer. You know what I mean? And you really have to have an intuition for it. Like when I was in school, one of the best test questions I ever got was from one of my analog design teachers. And it was a question that had no numbers. And he was like, how do you start this circuit? Like, how do you get it going? It was like some kind of band gap circuit. And it was like, you just had to sit there and think like, okay, if I pull this node down and then pull this node up, and like, I feel like that's like the intuition that analog designers have to have. But now you're going to get all the digital people to hate me.
No,
Sorry.
no, 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 no. But I was also curious, like, if it's harder for the manufacturing process, like if, for example, there will be more faulty chips
Oh, for sure.
for analog.
Yeah. So, do you want to talk about some of the challenges of fabricating a good analog
Yeah,
process?
yeah, we can talk. Yeah.
When you think about like, let's think about a digital to analog converter, a DAC, for example. One of the common ways that you'd build a DAC is you could use different sized capacitors that you switch in and out of your DAC to change the voltage that you're comparing something against. And so you would have, for example, a one capacitor here, and then that same capacitor you would have right here, two of those capacitors, right? This creates a voltage divider. Or you could do a resistor string DAC, like
Ah,
you've probably seen those, right? So there's capacitor voltage divider DACs and there's resistor string DACs. But think about if you're trying to fabricate that DAC on a CMOS process, what does that mean for your resistors and capacitors? They have to match because you're using unit size devices, but scaling them. Well, now what I'm saying is not only do I need to reproduce this one right next to it over here, just like it, but here, 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 right? And I could have what, 32, 64, I could have a bunch of those. And so any process variations. So now think about if I'm at the center of my wafer and I'm at the edge of my wafer, and my wafer is 8 inches, something like this. My capacitance value at the center of my wafer needs to be the same as my capacitance value over here. Well, what determines my capacitance value? The thickness of my inner layer dielectric. Well, how well controlled is the thickness of my inner layer dielectric from the center to the edge of my wafer? Or like wafer to wafer or lot to lot, right? So now the linearity of my DAC, which linearity of your DAC should look like this, right? As you're switching in the different bits or whatever, the linearity of my DAC is now dependent on the variation of my capacitors. So it's a challenge. Like it's not for the weak. Now, also think about an input amplifier or like a differential pair. So in analog design, you use differential pairs for everything, right? Well, a differential pair is just two transistors right next to each other that are supposed to match, right? So I would have two NMOS devices. They need to have the same threshold voltage, same drain current, right? Now, again, same analogies of like, okay, well, if the threshold voltage of these two don't match, every time I put in a signal, I am now getting the signal plus whatever mismatch is
mm-hmm.
present on my transistors. So it just turns into this whole big nightmare. Now, there's a lot of really good analog layout techniques that people use that you can make things match. So you use symmetry when you're doing the layouts so that you have the same metal lines, you have the same, the capacitor here sees the same topology around it that the capacitor here sees. Like there's all these cool tricks. And again, these are all things that analog designers just have to know how to look out for. And most of the time you learn the hard way.
Yeah, this was interesting because when I was talking to someone about designing chips, then
Yeah.
he exactly mentioned this. Like you can't say like I'm going to use 10K resistor and then 15K. No, no, no. You have to use same resistor all the time and build
Yeah.
the value
Yeah.
from these existing resistors.
Yeah. 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 I think if you go into that world, you kind of realize, if you came from like PC, like you've designed PC boards before, you're kind of spoiled because you like pick these off the shelf components that have great tolerance. They have like absolute accuracy, right? And you're just like, I want a 10K resistor. And then you place it, you solder it, you're good to go. It's like, you want to design a 10K resistor in the fab, you have to think about it a little bit, right?
And then also I heard some of these things, they add some kind of supporting circuit, which is then used maybe for tweaking or measuring and setting up some special registers to actually then somehow tweak the circuit.
Yep. Yep. Yeah, so there's a lot of if you have a process or a platform or like a CMOS, sometimes they call by the way, if you have like sometimes they call these platforms, right? So it'd be like a process that's owned by a fab that you're designing into. So the platform would have like a specific application, maybe like, automotive or cellular or whatever. So if you're designing into a platform, they might have like really cool resistors made out of like custom materials that you can like laser trim and stuff like that. A lot of times people use like one-time memory storage to do some calibration on their chips right
This is
after they
exactly,
test it,
yeah.
right? So I would say that it is interesting that with every new challenge that I see designers face, people come up with really incredible solutions to figure out how to work around it and squeeze amazing performance out of chips. So like, yeah, both digital and analog designers do that.
Okay, we can continue. We can continue.
Sure. Okay. Okay. So we had made our so N, by the way, N plus just means heavily doped N. So lots of electrons are available for charge carrying. N minus would be like the N well. Okay, so now we've created the N plus diffusion. We're going to do the same thing and create a P plus diffusion. So again, the P plus diffusion is my low resistance contact to the substrate for my NMOS device. So again, that way I can control the body of the device. The threshold voltage isn't changing on me. And then it's also my source and drain regions for my PMOS device. And then top down, here's what that mask would look like. So we're really close. We've almost built transistors. Now we need to be able to connect it to the outside world. And the way that we do this is first we're going to lay down a layer of oxide on top of the whole thing. Oxide is our favorite insulator. And then we're going to drill holes through it. And the holes are going to go, as you can see here, they're going to go to the well taps. That's what these are called. It's going to go to the source, to the drain. I'm going to have connections to the poly gates. And then I'm going to fill it up with metal.
Drill, you mean like it's like a laser will do that, or what does it mean, drill?
So there's different ways, but like for this example, I said sputtering. So what they'll do is they'll like, once you have your patterned wafer, you'll stick it into a chamber and like your wafer's sitting here and you have this, they call it a target. It basically has the material that you want to deposit. And then you shoot this ion gun at the target and then it like sputters down onto your wafer. I don't know how people come up with this stuff, by the way. But it works. So now that you have these contacts, so I would like to differentiate too. So the contact is the layer of metal that's vertically connecting to the transistor nodes itself. So source,
in that axis, yeah.
Yep, it would be like this. Then you're going to have metal layers that go horizontal that you use to connect the different, PMOS or
Tracks.
tabs, PMOS devices. Yep, exactly. Like you would lay out on a PC board, right? And then just like a PC board, we also have via layers. So we'll have typically multiple layers of metal. For like a 90 nanometer process, you might have 7 layers of metal, right? Because you're trying to route a ton of stuff. And so contact means you're going to the transistor. Via layers mean you're going in between metal layers. So it'll go contact, metal 1, via 1 to metal 2, via 2 to metal 3, right? All the way up to the very top.
I think there are a few interesting things what I would like to mention, what I learned before when I was doing videos. So the components, these transistors, are only on this one layer where the silicon is, correct? We can't build transistor about the transistors.
Right. Yep.
And
all your active devices are in the silicon. So diodes, right? BJTs, FETs, all in the silicon layer. Your capacitors, you could probably put anywhere, right? You can put those between 2 metal layers. That's fine. Resistors, you can do weird stuff with too.
And then also what was interesting for me, the size of these elements has to grow with the layers. So the lowest layer can be the smallest one, but I think the highest layer can't be as small as the first one, correct?
Right. Yep. Yeah, and they're doing a lot of interesting stuff today. They do like really like you'll have really thick top layers, right? And you need that because oftentimes you're taking like power off chip and you're bringing it onto the chip, right? And so yeah, it makes sense, right? That the metal layers at the top need to be thicker. A lot of times the inner layer dielectrics are thicker as well, right? Yep.
thicker, it means also the minimum width must be then.
Yep. Minimum width, minimum spacing, and then thickness of the layers in between, thickness of the oxide in between the metal layers, I would say. Yeah, that to be more precise, yes.
Okay. Do we have anything else here? So we basically did we finish the connections?
So yeah, so we have built our transistor, and so if I were to now, this is what it looked like from the side. Here's what it would look like if I'm a designer. So if I'm a designer and I look at a layout, the blue is my power and ground. That's like my metal routing. And then you can see that I have contacts. That's the black squares are the contacts. This is my poly gate. So I'm just connecting my transistors directly using poly. By the way, you'd only do this if they're like super close together, because poly has a higher sheet resistance than like other, like metal, right? So okay, so here's why I say analog designers have it harder, because this is what they do for digital designers. So digital designers get something called a standard cell library. And what that is like not every, but almost any type of logic cell that you need is already laid out for you. So you'd have NAND gates, NOR gates, inverters with multiple inputs, right? And they're all set this distance between ground right here on the left, this physical distance between ground on the left and VDD right here on the right is a standard height. That's why it's called standard cells. So I can just grab a NAND gate, grab a NOR gate, stick them together, and they just automatically line up, which is super cool. Whoever thought of that, genius. And so typically, if you are working with a fab, you need to know all of the layers for their particular fab that you need to build the transistors. Do you want to move into
Yeah,
talking
so
about
this was my next question. So we
Yeah.
talk about the process.
Yeah.
We know what we need to do, but
Yeah.
it's more complicated, because if we make these places a little bit bigger, parameters of the transistor are going to be different. If it's smaller, it's different. So, and also we don't know yet the capabilities of the manufacturer. So how this is actually done? I know how it is done. There is some kind of standard, correct?
Yeah. Yeah. So basically all the information that a foundry needs to communicate with the designers so that the designers can build circuits and predict their functionality is contained within a PDK. And a PDK stands for a process design kit. And basically it's a group of like files, data, and then some kind of tools that the foundry will give access to for the customers, and the customers use that to design their integrated circuits. So it's basically like the connection between the designer and the fab.
So there are for example, there are the rules, capabilities. So they will specify what they can manufacture, because not everything can be manufactured. I don't know, smallest clearance between tracks on layer 3 or something.
Yes, exactly. So so if we start there, so we start with the design rules. So the design rules will go through, and so remember right here we laid out which layers we need to build a transistor. Every single one of these layers in the PDK has design rules associated with it. It'll have minimum widths, minimum spacing. For transistors, you'll have minimum spacing between wells, right? Because they need to be isolated. By the way, one thing we didn't talk about is how we isolate transistors, since they're all in the same substrate, which by the way wouldn't be true if you used a silicon on insulator substrate, but we can get back to that. But the design rules are for every single layer, minimum spacing or maximum width. For metal layers, there's maximums that you can have because of electromigration, stress, and things like that. And so you'll have design rules, you'll have the models. And now the models are basically what the designers are going to use so that they can simulate their circuit. So what needs to be in a model is a really interesting question, because the model should one, be continuous, meaning that it doesn't matter if I flip from, like, for example, a transistor acts like a resistor for a little bit and then it acts like an amplifier. That transition between acting like a resistor and acting like an amplifier needs to be smooth. So the brainiacs that came up with the different types of models make it so that it doesn't matter which mode you're in, your models represent your device's behavior and they have smooth transition so your simulation doesn't crash. Your models have to be representative of your parts over all the corners of the process, meaning the corners of your process are, we had talked about like maybe a thin oxide in the center and a thicker at the edge. Well, that's not the only issue. You could just have a thinner oxide for that lot, right? And maybe a thicker oxide on the next lot. Those are the corners of your process. And so what happens is if you have corners of your process, you have devices that are operating faster or slower. For example, if I have a thinner oxide, my my NMOS devices have a lower threshold voltage. They could have a higher ID sat quicker, so they're faster. So that's my like fast corner, right? And so your models need to reflect not only your like nominal device behavior, but the variation of the devices over the corners. And then statistically, because we'll also do Monte Carlo simulations, like what does the variation of the transistors look like as a whole? And so your designers have access to basically your best understanding of your device performance. So that's what the model.
So it's not only about, I think your camera blurred when you, okay, it's focused now. So I can see there are also libraries. So I would like to mention first libraries. Libraries, it means these are the kind of what you already mentioned, maybe like already created transistor or inverter or something like this. So people or the chip designers, they don't have to draw it all by hand.
You have to drop it. Yep.
But they can just drop it. And I understand models for this. We will need models for this to simulate the circuit when we build it, for example, from the gates. But you also need models for like analog circuits, yeah? When you are building.
Yeah. So I do want to make a distinction there. Everything I was just talking about is like at the transistor level. But for the standard cells, there's different models. There's
okay.
models of input and output capacitance, timing, things like that. Those are separate, right? Because I will say the analog design flow is going to be different than the digital design flow. Typically, digital designers will start like with code, right? And they'll design everything that way. Analog designers are going to start with like a small cell and then kind of work their way up. A lot of times they do what's called top-down design methodology, where they have the system. They might describe it using Verilog A, which is the analog Verilog, and they'll have code descriptions of the functionality of each of the circuit blocks. Then they go in, design the circuit block, right, with the schematic and everything, and then take out the code version from their system level design and drop in the circuit version. And now they're simulating their circuit in the context of the system, right? So analog designers have a little bit different of an approach than the digital designers. I will say for a foundry, you're providing both. You're providing the standard cell library that has all of the simulation capabilities they need to use whatever digital tools they're using. The digital synthesis tools is what they use. And then you're also providing the specific models for like the analog team, where, they're dropping in the individual MOS transistors, right? And playing with the sizing and the bias and all that.
And I heard this is really needed also because once you build your circuit on silicon, then actually you need to some kind of simulate it and then go back, because some of the elements, they can influence each other because they are very close. And for example, suddenly you have there capacitors which you didn't want to have there. So all this has to be simulated, correct?
Yeah. Yeah. So you have such a good intuition for this stuff. I love
No, I know this from previous videos.
Nice. Yeah. So like, so this flow right here that I'm showing here on the right, this is from a Cadence blog, and they kind of go through, this would be like for an analog method, I would say, but they're going to start with like the specs and then do like create the symbol for it and the schematic and all that. Did it meet the specs? Sure. They're going to do some simulations. So they'll create a test bench, drop in their circuit, right? Test it over the corners of the process, test it using Monte Carlo simulations, right? And then they do the layout. And then what you're talking about right now is this step, physical verification, DRC, and LVS. And so first they make sure that physically what they laid out passes all of the design rules. That's DRC. Then they make sure that what they laid out actually matches the schematic, because there's a chance that like maybe you dropped in a metal line to the wrong side of the transistor, and so that's layout versus schematic check. But really important is parasitic extraction, which is what you're talking about. And that is where physically all of the metal lines, all the poly, all of that has resistance and capacitance elements, parasitics, that are unintended, right? But they do impact circuit performance. So you do this parasitic extraction. And again, that's the foundry understanding their process well enough, modeling the parasitics. And then you take the parasitic extraction and you can put that back into your schematic and re-simulate. You have to do that so that you know, like, do I still meet all my timing requirements and all of that? So that's a great point. Yes.
And also, I think this simulation, they also include the kind of like manufacturing process tolerances.
Yep. Yep. And there's some other nuances there too, like not just tolerances, but like we have like you'll have rules for pattern density, because when you are like doing CMP, for example, if you have a high pattern density in one area and a low pattern density in another area, you can have the issue that the CMP over etches in one area and under etches in another. So all of the I would call it manufacturability, right? The fab is going to put in rules in their PDK that make it so they can actually manufacture your design. So prior to a customer submitting, for example, a layout, to the fab, they're going to go through all of these checks. They're going to do the DRCs, the LVS, the density rules checks, and make sure that their design is actually not only what they intended, but manufacturable by the fab.
And I think you can include also some kind of like, for example, temperature influence or this kind of stuff in the simulations.
Yep, exactly. And like, again, all of that data comes from the models, right? So in the fab, there's individuals that specifically extract models from real devices that are fabricated. They extract data at all of across the entire temperature range that the platform is rated for, whether that's cryo or military spec range, whatever. They're going to extract all the data they need to correctly model the device performance across the entire temperature range. The fab is going to always model the transistor level. The circuit designers simulate the circuit level using the transistor level. And so, prior to going to production, your fab is going to take this array of devices of different sizes, different geometries, measure the characteristics of each one, and then at different temperatures, and then across different process SKUs, right? Fast, slow, whatever corners. And then from there, extract the models. And then what they'll do is they'll fabricate a bunch of wafers that have, fast devices, slow devices, and then verify that the models actually match. We call that like a silicon validation report. It's basically like, do our models really match our silicon? Then that's like a common part of the documentation that might be part of your PDK. So that's all stuff you can look up. I will say, the designers that are like the best designers are always the designers that like read the manuals. You know what I mean? Like they've read all the documents. Like I just feel like it just puts you at a different level, because there's so much good information in there. Like it's nerd stuff made for nerds, right? We're like, hey, you want to know what else we learned? And we just put it in the PDK. So the documentation folder is like where you can learn so much, because a lot of times there's like, a user guide, there's like tips and tricks, and
Did we forget something? Parameterized
Let's see.
cells.
Parameterized cells. Yes. So a parameterized cell is basically, if like imagine again, I'm building like an amplifier, for example, and I just put in an NMOS and I'm trying to size it a certain way. And I'm like, okay, I want it to be like, a 10 over 0.2, whatever it is. When I go from being in the schematic environment to creating a layout, a parameterized cell will basically take the schematic entry that I have and create the layout that matches that device.
So, for example, I would like to a transistor for 3 amps, or I don't know.
Yeah.
Okay. So
you would pick the W over L based on those specs. But yes, exactly. Yep.
Okay.
So
And
W is like so I said W over L, that's like length and width of your device. So length and width just determines like I the current capabilities of your FET. So yeah, so basically parameterized cell is just saying you don't have to do the hard work of laying out every single square. Like I don't have to lay out N diffusion, P diffusion, contact, poly. It's just like it just appears, it's the correct device, it's the right size, matches my schematic, good to go.
because you even wouldn't know exactly maybe how big openings you need to do, because you would need to do some calculations or something to be sure you are designing correct transistor with specific parameters you need. No, otherwise you would
Well,
have to calculate it somehow.
Well, yeah, so like as far as like the W over L sizes that you'll pick for your transistor, that's going to be set by your spec, right? So if you have a spec for your amplifier, you know you need a specific GM or a specific current, you're going to calculate the size you need, then you're going to simulate it and if
Oh, so
it's the
you
right.
have to calculate it.
Oh yeah. Oh my gosh, there's so much math. Yeah, you have to calculate. I mean, I don't know, maybe there's analog designers that don't have to, but I always had to like sit there like, uh you have to go through like some level of hand calculations to kind of get a feel for where you're going. Like I don't maybe the younger generation doesn't. Maybe they're just totally like simulating everything. I don't know.
I thought you place something into your schematic and you double click and you just put there like I need this current, I need this
No, no,
voltage.
no, 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 no. So, no, you can't do that. That's not the way it works. No, so you gotta go like typically you'll work backwards from some specs. So like for amplifiers, for example, if you know you need a specific gain, you can back out from that gain like the physical sizing of the transistor, the W over L. And then you'll put that device into your schematic, right? You'll simulate it and see, oh, does that work? And oftentimes you'll find out like, oh, my transistor isn't the right size, or I didn't bias it correctly. So bias just means what like mode your transistor's in. So you can think of bias as like you've already turned on your car, but you put it into a specific gear, like first gear or second gear. That's bias for a transistor. So yeah, no, it's a whole thing. That's why I don't know. I have compassion for analog designers because I feel like it's just like it's an art form.
Okay,
There's
now
actually a book. I don't have it right here, but there's a book I have. It's like it's the art of analog design. It's because it's like, it's a whole thing. It's black magic.
I maybe that's why I do digital, because I'm not so clever.
Oh no. No, I mean digital is its whole thing too. Someone was talking to me the other day about like SerDes stuff, and I was just like, I was like, can you explain this with crayons? I didn't get it at all. So it's a whole thing.
I don't know why. I always because I think I was always fascinated with software, and basically digital design is very close to software, and that's
Yep.
I think why I like it, because I remember when I was young, I always wanted to design my own computer. I wanted to design PC
Amazing.
motherboard, so
Oh, that's cool.
that's what was fascinating for me. Okay, so what I would like to make,
Did you ever design one?
couple of, yeah.
Nice.
Yeah,
That's cool.
and then I didn't know what to do next, because I already I did it, so what next? So then
Yeah,
I
yeah.
started teaching about it, how to do
Oh,
this.
nice. It is interesting. You don't realize the gaps in your own knowledge until you have to teach something. Don't you think? Like it just highlights, you're like, oh shoot, like what are the details here?
Uh, what I wanted to ask is, so how long this process takes? Because I know it can take a long time. It's not days.
Yeah, so I mean, so it it can take anywhere from like a couple months to many months, right? So this is not like a quick turnaround thing because so so big picture, the designers need time to simulate and build their circuits, do the layout, verify everything. Once they submit their design, then that design gets transferred from layers that are in the PDK to physical masks that can be put into the fab, right? Those are called reticles. And then those physical reticles are going to be used throughout the fabrication process. So, I mean, anywhere from like 2 to 6 months, I would say. It can vary a lot. It varies based on the foundry, the complexity of the process. There's some processes that have like 200 steps, right? That's how I put it.
200.
Oh yeah. Well, I mean, because this whole like resist, deposition, remove the resist, deposition, remove the resist. I mean, that's just 2 steps, right? It's 6 actual steps, but that would have given me 2 like diffusion opportunities, right? So I mean, it takes hundreds of steps to make these transistors.
So to make chip,
Oh, I'm sorry. Let me rephrase that. To make the entire wafer, like
uh,
not just the transistors, but yeah.
we didn't make the chip yet. Then it has to be tested, cut it. It has to go to packages and
Yeah. Yeah, so long term, like the life cycle of the chip could be something like, okay, so say I've fabricated all the wafers in the fab. It took me a couple months, but I've done it. Now I'm going to do my electrical testing. This is just kind of like making sure that my process is centered. So I'm testing, remember those test structures that are in the streets? That's this right here. Um, right? So there's little test structures that are in the scribe lines. I'm going to test those on some automated prober. I showed this one right here. This isn't for production. This is for R&D, but and the probe that you use is dependent on what your application is. So like RF applications have different probes than like DC parameters would, or like analog processes that aren't RF would use. I should say low frequency processes. So, okay, so I'm out of the fab. I have a wafer. I'm going to do electrical testing to just make sure that I fabricated it right. This is like does this product meet my specifications, right? I'm not testing the customer's parts yet. Then maybe as a foundry, I can test my customer's part, or maybe I can't. So either way, typically what you would do is take the wafer, knowing it has passed your electrical test, and now you're going to try to test your parts. So there's kind of two categories there. One is what they call design verification testing, and this is where you're testing every single aspect of your design to make sure to verify that it works the way you think it does. So this is like the more rigorous test. You would do this on, like, if it's a new product, you're going to do DVT on it. And sometimes DVT is at bench level, just because it can be really tricky. And then typically your binning criteria, like whether you bin a part as good or bad or fast or whatever, would be done at the wafer level, and it's a subset of those DVT criteria. So I pass electrical specs, that tells me the foundry built it correctly. Now I need to pass the design specs, that tells me that the designer and all of that did their part correctly, fab built it correctly. Once I have known good die, so typically they like ink the die that are bad. So they'll go through, right, and they'll just put a drop of ink on all the bad die on the wafer, and then they'll store it as a wafer until they need it. They being whoever's going to package it. Once they need it, they'll take it out, they'll chop it up. So a lot of times they'll use like a diamond saw with some water, right? And they just go zoom, 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 down all the streets, right? And the wafer is stuck to like this like plastic material so that the pieces don't go flying everywhere.
I was
Right?
exactly thinking about this, like if it's not going to damage the
Yeah.
chip.
Yeah, they call them like chip outs or things like that can happen when you like sometimes if you have a saw that's like not sharp enough, it can like chip as your wafer. So that's why you need your streets, your scribe lines to be big enough that your saw can go through it without getting any of these little chip outs. So yeah, so they dice it up, and now it's on this sticky thing, and it's all singulated die. So then they use what's called a pick and place tool, and they pick up an individual die, drop it in a package, pick up an individual die, drop it in the next package. So once they drop them in the package, then they'll like wire bond it. And then at that point, typically it will go through another set of tests. Sometimes it'll go through that set of tests after the lids have been sealed onto the component. And that set of electrical tests is a subset of the wafer level testing, right? Because they already know the part is good, right? So the question they're trying to answer at like the package level test is like, did we screw anything up by packaging it? And the answer sometimes is yes, right? But most of the time, like you do a pretty good job, but you'll lose a couple die here and there because something went sideways. So that package level testing also occurs on automated probers, and it's interesting with those because the part is now like a physical part that'll get dropped into like a socket almost, right? And then you'll have these big PC boards and all that. And then after that, typically, I mean, it depends, right? You can have reliability testing, you can have radiation testing. There's a lot of other testing that can happen. It just kind of depends on what your application is. So it never
So,
ends. Testing never ends, Robert.
okay, mm, let's say we are going to manufacture a chip which was verified. We
Mhm.
send data to production. How long it takes from taking the data and getting the chip in ready chip? How long it can take? I'm just curious.
Like in package form.
Yeah.
Oh man, I mean, if you were going super fast, like maybe 8 months, but like if it was a prototype, like 12 months, I mean, it can take a long time, right? Because every step is like,
How much does it cost? I'm just curious.
a lot of money.
It's
So,
in millions, yeah. Or I think there are more
well,
ways. There are more ways how you can do it because I think there are also like services, shared services or something.
yes. Yep. Yep. So there's a couple things there. So typically if you have a new product that you're trying to introduce, you don't need that many parts, right? But the barrier to entry to that is a little high because your reticle set, those initial reticles that are going into the fab, those are very expensive, right? And the first time setting up all the recipes and doing that stuff in the fab costs more than the production level stuff will
Hmm.
do, right? It's like the first time you do anything, it always takes a little bit more time, and then after that, you know how to do it, right? Because everything's already set up. So I will say, once you're in production, the prices typically go down. What you were just talking about are called MPWs, multi-project wafers, and that's where a fab will offer like area of silicon that you can design on, and then they'll just ship to you. So, for example, you might get like a 4x4 area of silicon, and you'll get 25 die shipped to you after like 5 months or something like that. And the cool thing about that, by the way, is that some of the foundries will use open source PDKs. So they're like two big um, like CAD companies. There's Metagraphics and Cadence. Sorry to all the other companies, but those are the big ones. And they're expensive to get their licenses, right? So the cool thing about these open source tools is like you can just download on GitHub some interesting libraries and things like that, and then just run with it. Depending on the fab, I mean, you could get die for a couple $1,000s. So like a lot of research universities will go that route. They'll
Hmm.
use MPWs to like fund their research. I do know also in America through the CHIPS Act, there was some legislation to support um, what they would call, what did they call it? It was like the lab to fab like death zone. I don't know what it was called, but it was basically like someone has this great idea, but actually getting to the point where you can fabricate it is really hard and really expensive. And so they were like, how can we create test vehicles that people can use to easily evaluate their chips and do it cheaper, right? And so basically, you as a fab would design these little test vehicles, and someone could have their die designed into it and know how to test it, and all that stuff would already be done. So I think things like that are a good idea. It's just they're really hard to create and make them like ubiquitous for everybody's different,
Hmm.
everybody has such different needs, right? So yeah, expensive. Sorry. I don't know like exact numbers,
No, no,
but
no.
it's expensive.
I think it's good to point out that if someone is really interested, uh, then these simple shared things they actually starts around
Oh yeah.
thousands. So it
Yeah.
is actually possible to manufacture your own chips. It just it's just not like direct communication with like chip manufacturer. It goes somehow through other companies, correct?
Yeah, yeah. Well, so like the company I work for does both like manufacturing for production, but we also offer MPWs, right? And
Oh,
like the Moses service offered MPWs for a long time too. We work with them. So there are still fabs that will do the MPWs. Um, I would also say that like driven, curious people are always going to figure out ways to get things done. You know what I mean? Like, and also FPGAs are cool. Like, I almost feel like those aren't used enough sometimes when you're trying to like figure something out. Like FPGAs are amazing. I don't know. So yeah,
uh,
I think there's lots of lots of good ways that you can you can build that stuff. If I were doing it and I were trying to do it on the cheap, I'd become a student, right? Like go study at a university. I'm like, and like Cadence gives the universities a free license and then they get them on these MPWs. So go be
I
a
was
grad.
asking if there is someone else in the way because it may be expensive doing support, to someone who never designed chip before, no?
Yep. Yeah. Yeah. Well, and here's the other thing. You don't know what you don't know. You know what I mean? Like if you've designed it, like I had a grad student that I was helping them with the design and they didn't put any pads on their chip. I, I was like, where are the pads? And he was like, what pads? I'm like, how's your chip going to talk to the outside? It was just not something you thought of, right? And it was just an experience thing, right? And so that's the tricky part is if you're like, what's the lowest barrier to entry if you're trying to
Yeah,
figure
that's
this.
what I meant. Yeah.
Yeah, it's probably an MPW. It's going to cost you a couple $1,000s, and you're going to get back a little die that you're going to have to figure out how to test. But all of that stuff you can do, right? I mean, you can design a circuit board for super cheap, drop the die in directly, wire bond the die directly to your PCB. I mean, it wouldn't be the end of the world unless you're going for super high performance, but
And I think when you mention FPGAs, I think some companies they would like to use chips because of IP. Maybe it's a little bit, and it can be also cheaper. Maybe because FPGAs are quite expensive, and if
yep.
someone come up with idea for millions, then it's maybe cheaper just to manufacture chip.
Yeah, so IP is a good topic because, when you have access to a Foundries PDK, a lot of times you get access to some of their IP as well. So they might have analog blocks already built and characterized for you. Um, and again, that like speeds up your design process, lowers the risk of your design, right? And I think overall that's good. So definitely like paying for some of that like upfront does make sense if you have a design that's high risk or you're new. Um, yeah, it is tricky. Like what kind of design is someone who's just getting into this trying to do? Do you know?
I think people are just interested in. They would
Yeah,
like to design their own chips.
their own chips.
Yeah,
Yeah.
that's what I think
So
is attractive.
there was I'm going to get the name of the company wrong, so I don't want to say it. There was actually there's an RF company that had this idea where they were like, look, we know people want to build their own RF chips. And so we're basically going to create Lego blocks of components that they can put together, right? So it's like you had an RF amplifier, you had this, and you just like get the pieces and put them together. And like, I think that's a cool way to do it. I kind of wish more fabs would do it that way, almost like, you know, if you like, to me, the thing that would be super useful for the majority of people, to me anyway, is like it's not just giving them the die from like a MPW run, but like a test board
Mm-hmm.
that they can put the die in.
Mm-hmm.
Because like I know for me, like getting a die wasn't the hard part. It was
Mm-hmm.
like all of the steps after so I could actually test what I was trying to do,
Mm-hmm.
you know? And even when I worked in industry, right, it was like there were times where I would randomly just have to design my own board and I'd go like beg someone to let me into a lab that wasn't mine. I'd be like soldering stuff. But maybe the average person doesn't have access to that stuff. And so if you as a foundry could just give them a board with their test chip, that'd be pretty cool. And
Yeah,
I
because
think that's what the TVIP program was trying to do in the CHIPS Act. I just don't know that they've gotten a lot of traction yet.
mhm. Because you are right. Because maybe you are or someone is into designing chips, but to get the chip, it requires also designing packaging and then
Oh
also
yeah.
do the packaging
Yep.
actually. So it's another step, and then also they have to somehow get the board where they are going to
Right.
solder the chip and test it.
Well, and now think about the expert you have to be in all those areas, right? Because now no longer you're not just an analog designer, right? You're a packaging expert, you're a board layout expert, right? Like how many little tricks have you learned about board layout over the years, right? And now that person who was trying to design a chip has to go figure that stuff out. So yeah, there's a lot of
Exactly.
challenges.
what else do you have in your slides? Did we skip something?
Oh,
What
I
is on
don't
the
know.
first one?
Let's look. Oh, okay. Oh, so I had shared this picture just kind of like how people talk about foundries, just because, it's like how do you describe a foundry? You're going to talk about like what diameter they're using for the wafers, because that describes all the tooling that they have in the fab. So all these big giant tools that you see here are meant to process one sized wafer. Um, and the node, so node would be like if someone says like 2 nanometer or 4 nanometer. What that used to mean was how the minimum length of your poly gates. Now it's kind of just more a marketing term, because I don't think like 2 nanometer is like actually tied to anything that's in the platform, so that's okay. Substrate material. So again, this is going to be dependent on the application. So for RF applications, like I talked about, they're not using silicon, but for like TSMC, there's a lot of silicon going through. And then what often they're called platforms. So again, that's describing the different application areas for the specific technology. And so if if you were trying to figure out, okay, how do I build this thing that I want? Like a good place to start is knowing your application, and that's going to determine like some of the requirements as far as like temperature and reliability and all of that stuff, and like power consumption, all of that. Now you know the node that you need, and you can pick a platform based on that, right? I put in some keys to production here. I think these are probably intuitive, but like the dirtiest thing that's ever going to be in a fab is a person, right? So like no joke. So they really do their best to like minimize anyone handling the wafers, moving them. I don't know if you can see it in this picture real good, but this is a track right here. It goes through the fab. And so it's like a wafer tram. So like the wafer boat goes up there and it's like shoots through the fab, because you don't want people like walking around dropping your wafers. I've had interns do that. It's heartbreaking.
Oh,
And they have
someone was, sorry for interrupting. Someone, when I was doing one of the videos, someone told me that in factory, someone dropped the manufactured the whole box to ground, and it was like millions and
oh
millions
yeah,
in expenses. Like,
yeah. So when you first get the wafers, the starting material is kind of cheap in quotes, right? Like a couple $100 maybe for per wafer, probably less. But every single layer, you're adding like, so by the time you get done processing hundreds of steps, right? And it's been in your fab for months, that could be $1 million, right? Millions of dollars.
and if
Yeah.
you have
So
more of them stacked in one box, it's like,
yeah, well, typically you'll have in one boat, you'll have an entire lot. So a lot could be 25 wafers. So yeah.
uh,
I have never dropped something in the fab, but also like that was one of my biggest fears when I was working in a fab. I was like, please don't, because I'm pretty clumsy. I was like, oh my God, please don't drop.
I remember I had a question about this special tool. What you say it's used to make the mask? How you call them?
Are you talking about the reticles themselves,
Yeah.
or
So
what
what
tool?
exactly it is?
Yeah, so the reticle kind of looks like it's about this big, like well, depending, but and it just looks like a weird pattern on it in metal. And so basically all it is the physical, or I'm sorry, the drawing layer from the PDK that you used, that is shared with a reticle like producer. So the reticles come from a third party, and that literally all they do is they print metal layers onto this like glass, and that's the reticle. So you would like have you'll have the shape of whatever you're trying to build in the fab for that particular layer. So for example, one, and then every single layer that you need to build in the fab has its own dedicated reticle. So for you, my customer, if you have a design, you also have a set of reticles in the fab that is your NDiff, PDiff, poly, contact, and those all go together as a group, because I'm going to need all of those to make your product, right?
This is interesting. So it's basically like film in PCB manufacturing, or like stencil or something.
Stencil. Yep,
Yeah,
exactly. Stencil. Yep,
yeah.
exactly.
And so this is expensive. Manufacture these stencils is expensive.
yes, it's not the most expensive part, right? But it's expensive. There's like all of it is, man, nothing's cheap. Like you have to get the reticles, right? You have to set up the process flow that you're going to use in the tools. So it all has to be automated, right? So there's a list of steps that your product needs to go through. And it can't be like some person in the fab going off of their own checklist. It has to be like Intel would say, copy exactly, right? It has to be a known process that you're using. So every step is written down. So it tells like the operator, take this boat, load it into this tool, push this button, get this recipe, go, right? It has to be totally like that. And then it's like, okay, when it's done, push the done button, like, and there's an MES system that like tracks all of these steps, right? And make sure that you're going through them. So um, there's a big push to get people out of the fab as much as possible, I would say. But you know, like Intel, for example, TSMC, like you want people in the clean room as little as possible.
But so this is interesting because I thought it's some kind of laser which will draw the motif or something. So it's not laser.
No, no. So again, it's that resist layer, right? So they put the reticle up here and then they blast with UV light, and then whatever is exposed, like the UV light goes through the reticle, exposes the resist is exposed to this UV light, you develop it, and then you get the shapes. I
This is
will say, so Lam Research, they're a big they're one, I think the biggest manufacturer of these tools that do the litho. The guy that founded that company recently went and founded a different company that is doing what you're saying, which is laser drawing every layer. So it's kind of funny. He went like the opposite way of like his whole bazillion-dollar company did this great thing with, you know, reticles and stuff. And now he's like, let's try it a different way. So,
I'm asking this because I know when I visited PCB manufacturers, then the old
mhm.
way was using UV light, but the new
Okay.
way is the laser because it's much faster. Like they don't need to store the films, and also it's direct exposition. No one is touching anything. Like it just goes through machine and it's exposed.
Yeah, and I don't know like I don't know the comparisons that you can make on that method for a
Yeah,
CMOS
chip is probably
process.
very, very small. Maybe laser would be, it's difficult to use because laser has some diameter, maybe, I don't know.
Yeah, well, they run, I mean, the feature size, that's what they call like the minimum size of the like gate poly, for example. The feature size is so small that like the wavelengths of light have to be tweaked, right? So like they would do stuff where they would submerge the wafer so that they could get like there's just all this, they have deep UV stuff. Like there's all this crazy games they have to play now to print the feature sizes that we have today.
Oh,
I guess the other thing too with the PCBs is like there's not as many layers. So I do wonder if like you run into that limitation with the lasers, if you have to like print every single layer and there's like, you know,
I don't know.
a
But I
lot
didn't know
of
about submerging. I know I have microscope. So if I would like to see something with resolution higher than 400 or something, you should use oil or something because the light
uh-huh,
will bend and you don't want
uh-huh.
yeah. So maybe that's something similar. I don't know.
Yeah, yeah. Yeah, they play the litho people play all kinds of tricks. It's wild. And by the way, if you see a picture like this with yellow tint, it's a litho area.
Mhm.
They use
Uh,
like yellow lights above.
okay, what else we skipped?
I don't know. Let's see. Okay, so what else did I have? So we already talked about, I'll just go through. We already talked about these. We know everything about FETs now. So I think I had shown this just
Oh,
to show.
capacitor resistor. Yeah, interesting.
Yeah. Yeah, because um, you know, one of the things that I think is fun for people coming from a PCB thought process to ICs is like, how do I get all the things I need in one place? And it's like, okay, like how do we build resistors? How do we build capacitors and diodes? So anyway, yeah, so that's why I included this. But
Explain. I'm curious.
sure. So there's lots of different, so a couple of ways I can explain this. So the first thing is like the shape of a capacitor. So you can build capacitors different ways because capacitors are just some kind of conductive layer, an insulator, and another conductive layer. So you can build things that are like in long lines next to each other. Think of like, or you can build things that are like interdigitated and use coupling capacitance between the interdigitated fingers to build it, right? Or you could just use like parallel plate capacitors. So there's lots of like fun games that you can play to build the capacitors that you need in a CMOS process. The challenge, and we talked about this earlier, is you have to deal with these kind of 4 key issues: parasitics, which is unwanted capacitance, matching. So again, we're always using a unit sized capacitor and then scaling it, like just repeating it multiple times to get bigger versions for analog designs. So matching is a huge problem. Absolute accuracy, this is more of an issue, I would say, with resistors than capacitors. Resistors are trickier. And then temperature coefficients. And you had mentioned this earlier, right? It's like, how does my circuit change over temperature? So those are kind of some of the things that you think about. So I would say that depending on the platform you're talking about, they might have really good resistors or they might not. But what's cool about what's happening today, I would say, is there's a lot of like thin film resistors or like hybridization that's happening where it's like, okay, I can't get the resistor that I want on my chip, but I'll literally like get the resistor I want and bond it physically to my chip. And we see customers doing stuff like that now. So I just think people are like getting creative for how they can get all of the functionality they need like on their chip. So
they finish the chip and then they solder the resistor on the top and put everything into one package, or
they don't solder it, they glue it.
glue it. Okay.
Yeah. So, and then also we have like people used through silicon vias. And so that's basically where in my, if this is my integrated circuit, I'll have a via that goes all the way from the top to the bottom of my circuit. And then I'll just stack this thing on top of something else. And maybe that has the thin film resistor. And now I have a via that connects between like some circuit, some other thing, and then the resistor I want, right? So there's like really creative ways that you can get at hybridizing not just your IC, but now connecting it with other cool components. People do this for like sensors and things like that when they're trying to like integrate maybe like a detector to some kind of readout or stuff like that.
Mm-hmm. So you can even drill through the silicon?
Well, it's not, we're not drilling, but yeah, it's like it's an etch process,
Mm-hmm.
right? It's a via that goes all the way through top to bottom through the silicon. The interesting thing is it doesn't go all the way, like physically, it doesn't go all the way through in our fab. But what'll happen is when we give the wafer to the customer will back grind it, and they'll back grind away a bunch of the silicon to get at the bottom of the via. So it comes out really thin, so they have to put it on something to give it mechanical stability. But yeah, it you get these really cool, and I shared this picture. It's kind of like a similar idea where they call it an interposer a lot of times, where you're basically having these via connections that go from one chip to another. But people are doing so much cool stuff with this right now. I know a lot of companies this is a big deal because they get memory, they get really good analog performance, they get like there's just so much. It's a whole like, I don't know, it's a whole system that they can get when they stack.
So it's basically very small PCB between different silicons?
But they don't need a PCB. They use silicon as the
substrate. Yeah. Oh, okay. Interposer is from silicon.
Interposer. Yeah. And there's companies that are trying to move away from PCBs altogether. And so they're trying to fabricate on silicon wafers the whole thing.
I've seen pictures like basically basically the silicon was kind of soldered to PCB.
Yeah, it's crazy. So I'm always amazed when I learn about these like new technologies because people just, I don't know, they're like fearless. They figure stuff out. I love it.
What else we skipped? 21. You didn't click on 21.
Oh yeah. Well, we talked a little bit about this. I don't
Oh no, we didn't. We did before recording that South Korea. I was not expecting they manufacture so many chips. So,
Yeah,
even more than Taiwan. I thought Taiwan is the biggest one.
yeah, I thought TSMC was the biggest one too. Um, yeah, it is interesting, and I think one of the things that the countries that are doing really well in this do is they make they call them like tech parks, where they'll take an area, like a giant area, and they will do the plumbing, the water, and they will build basically all the infrastructure that companies need. And so, say you are a company that makes chemicals for fabs. Say you're a company that makes tools for fabs. Say you're a company that makes reticles for fabs. They give all those people basically like a little bit of a discount to put their companies in this little park. And so not only are they making sure the supply chain is there for their fabs, but like the turnaround time is super quick. So anyway, I think there's a lot of incentivizing that happens in these companies or these countries that are doing really well as far as, well, I would say if you have a lot of IC manufacturing, it's a good thing. So these countries that are doing really well with that, they have a lot of ways that they incentivize the companies, and then they make it easy for them to have a supply chain that's local, that's right there, and getting rewarded for that. So yeah, we don't quite have that here in the U.S., but it would be interesting if that was a big push um, from the United States perspective, if they really did want to ramp up their presence in manufacturing.
So now I have one question and one note what I would like to point out. So we will go to question a little bit later, but so I don't forget why it's so hard to actually build this kind of like factory. But the second one was interesting when again I was talking to someone else or I was watching video, I don't remember, and they mentioned one of the very important things to build this company is like seismic activity in the area. Correct? I don't know.
Yeah, that's a good point. So I will say, so I was at have you ever been out to Berkeley, California? So
Mm,
they have a beautiful like nuclear lab out there, right? And my first day there, they give you a safety tour and all this stuff, right? And they take me outside and I'm standing here at this building, you see this beautiful view of Berkeley, and they go right down there, there's like a fault. So if there's an earthquake, we're all just gonna get sucked in and die. Who picked this building location? But yes, so to your point, you can think about like metrology or cross sections where they're trying to get an image of something really small, right? All of those tools are sitting on what they like, they'll take out the floor and they'll put in these concrete pads, right? And then the foot of the tool lands on a concrete pad so that if there's any motion in the building or someone walking by, for example, like it doesn't screw up what the tool is trying to do. So yeah, I could see that being an important quality. However, there's a lot of fabs in California, so I don't know, maybe not.
I don't know.
A
I
lot of,
think I just found it interesting, and I never thought uh, that these would play a role in deciding a location because
yeah,
yeah, because the process is working with so small dimensions that I guess
exercise, yeah.
any small movement can actually damage the process.
Yeah, and I think like big picture, it's hard to understand like the whole ecosystem, right? I think it was in 2020 where TSMC had issues in Taiwan because of like a water shortage. And you kind of don't always like it's hard to put together like all of those pieces that make up a functioning ecosystem for, being a good IC manufacturer.
So why is it so difficult to build more factories? Because because they have expensive equipment, or why?
Mhm. All of it. So if you picture like the fab floor, like what I showed you in this picture, um, right here. Underneath this floor is a floor that looks exactly like it, except this tool right here has like probably 10, 15 lines going to and from the instrument. Could be gas lines, could be chemicals, could be something,
Hmm.
right? Now, For this floor of the fab, I need the best filters the world has to offer because I can't have any particles in my fab. I have every single one of these pieces of equipment could cost $1 million, $5 million, depending, right? And that's just the tool. That's not counting maintenance on the tool, calibration, chemicals, like maintenance if something goes wrong. So now there's a whole line of these, right? So, and then underneath the fab, so I have this fab floor with millions and millions of dollars worth of equipment and the best filters, the right lighting, the cleanest people walking through the fab, right? Who are trained, who are the best software systems so that I understand the process flow. My recipes are up to date. I have a tracking system so that if there's any changes made in a recipe, I can track it. Now I go the step below the fab, and this is stuff that's not seen. I have a whole maintenance crew completely dedicated to making sure this tool never goes down, right? And they walk the floors below, right? And again, those maintenance people, they got to be the best, right? They got to know. And some of the chemicals here are chemicals that if they're released in the air, they kill you before you're dead, right? They catch fire in air, or you can't smell them. Like, I mean, so not only do you have a process that is specific, it's expensive, it's also there's a lot of safety issues. And so, I mean, if you think about what it takes to build a shed in your backyard, and you're like, okay, well, I need the ground to be flat, and I need, like, you start to think like, okay, there's some things I could think of, like it's like that times like a bazillion, right? It's like, I think 65, yeah, oh, I put it on here, $65 billion. That's this TSMC fab. And by the way, so a couple comments about this. So not only does it, like, this fab needs to have DI water. Every weird kind of chemical you've ever heard of in your entire life needs to be able to come on site, fill something up, and then leave the site. Well, logistics wise, how does that happen? Shipping, how do you get your wafers in the building and keep them clean? Do the steps here make sense? Like, are the litho steps, should they be all together? Should they be litho equipment be scattered so that well, now you got to take your wafers from this thing to that thing way over there that's in a different fab, right? Like, everything is expensive. So it's like, I think on a good day, it's a logistical nightmare. Like, on a bad day, it's like very dangerous for everyone because there's a fire, right? I don't know. Those are some reasons why it's expensive. Yeah, I would say the equipment is what makes it the most expensive.
Mm-hmm.
And I think that's where too, if you're behind in the technology nodes, that's where it's hard to catch up.
Mm-hmm.
Like, when it comes to being ahead, TSMC will probably stay ahead because they have the best tooling, right? And so if you're another fab, it's like, well, you have to get the best stuff to be the best, right? And so yeah, it's a high barrier to entry on these things.
Mm-hmm. Sometimes when I go to these big factories, like, again, I can only compare this with PCB factories. The logistic is exactly what I was thinking about. Like, they must not make mistake. Like, on one panel, there are multiple designs from multiple different people. And now there are multiple different panels going through whole process. And you need to be sure in every single process there are correct data. And in every process, which board is going through the process. And it's like,
Yeah. Well, and again, it's like, now think about your tool could have an upgrade, right? Could have an upgrade that it needs. How do you know that, right? So it's like so now every tool should have a tool owner, right? So it's like there's all these little details, that, yeah, they're not trivial.
I agree. What else we missed?
I think we might have gone through all of them. We went through testing. We talked about what it takes to build them. We talked about the passive devices, what it looks like when you start it, going through the process, and how to design it.
I think we went through everything.
Yeah, I think we did.
Now I'm curious. So what do you do actually?
What do I do? I ask myself this every day.
My wife, she still doesn't know what I do.
Oh, really?
No one knows.
Yeah. Yeah,
It's hard to
if you ask
explain.
my kids, they'll tell you I'm a scientist. So
Yeah.
I love that.
I say
You
I
know,
work on computer or with computer.
that's what you say? Okay. Well, I guess I would say like my key job is to help people that are designing into our platforms. So I help the designers, and basically why it's exciting for me is I get to learn what people are trying to build and try to figure out in advance where they're going to get stuck or have problems. Right. So for their specific application that's super nichey or going to be a challenge for our platform, how can I get ahead of that problem and help them figure it out? So I mean, that's what I do now. I think, yeah, my kids would tell you I'm a scientist. I think if you talk to any of my neighbors, they would just think I'm an idiot who can't take out their trash.
I,
So yeah, I don't know. It depends on who you ask, probably.
yeah, it's difficult. I remember we had family gathering, I don't know, a couple of weeks ago, and my wife's sister, she was looking at me and she said, "I still don't know what you do."
Well, can you do you ever say that like you do a like you have a YouTube channel?
Mm, I don't say that.
Yeah, I think you can call yourself an influencer, Robert.
But you know, when you tell these people, not everyone will understand it correctly.
Yeah, I would say like being an electrical engineer is like the quickest way to shut down a conversation. Like, you know what I mean? Everyone's like sharing things. You're like, what do you do for a living? You're like, I'm an electrical engineer. They're like,
Yeah.
anyway.
I have this broken computer or broken vacuum cleaner. Can you fix it for me? Like,
Yeah. Yeah, that I would say that my extended family thinks I'm just IT, right? They come over to my house and they start handing me things. Can you fix this? Can you fix this? I'm like, did you try turning it off and on again? Like, what are we doing?
uh, okay, thank
Yeah,
you so
I
much.
maybe I'm IT.
Thank you so much. I really had great time, and I learned a lot again. If some people, if people who are watching this video, if they have questions, if they would like to learn more about how chips are manufactured or anything about the chips, maybe we can create another video. They can leave comments and we can talk about this. Correct?
Wonderful. Thank you so much for having me, Robert. Oh gosh, yeah, I would love to come back.
Thank you so much, Heather. And yeah, I really enjoyed this time. Thank you.
You too. Bye.
That's all for this video. I hope it was helpful. If you would like to learn more about electronics and board design, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KeyCut, and also courses covering many different topics, for example, FPGA, EMC measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching and don't forget to leave your comments. See you in the next video. Bye.